Hello everyone. In today's problem, we are given an m cross n matrix that contains zeros and ones. Our task is to return the minimum distance from zero for each element. So for example, we have this matrix right here. We will get zero for any element that is zero because the distance will be zero. Whenever we have ones, we will have to count the shortest distance to any given zero. It could be coming from four directions, and we have to consider the minimum distance among all four of them. This is not true for the edge, as they have only two directions instead of four, but it is true for all the inside elements. Let's look at some of the constraints to get some additional information. The length of the row or the length of the column can range from 1 to 10,000. The other interesting thing is we can have up to 10,000 elements in our matrix if we combine m cross n. So in the above condition, if m is equal to 10,000, n can't be equal to anything other than 1 because it would violate the second condition. So if 1 is 5,000, the other one will be 2, and so on and so forth. The values can either be 0 or 1. There is at least one 0 in the matrix. That is a given. So we will have no condition where we have infinite distance to 0 in our answer. Coming to the approach, let's try to solve this problem. We will be using the breadth first search approach. The BFS looks very similar to the depth first search algorithm. The primary difference is we use a breadth first search when we are trying to find the distance from the root because of how the algorithm is designed. And DFS is used when we are trying to go in depth and trying to explore more things. So here we will try to do something almost similar. We will first mark all the zeros in the grid and now try to go in four directions and keep adding 1 to the distance. Now once you start doing this, you will realize that there is a problem because you start colliding into other numbers. What I mean by that is you will start bumping into integers you have already marked. To avoid this, we need to identify the vertices that we have already visited. We can keep track of the visited vertices. We keep incrementing our distance from 0 by 1. What this ensures is if there is a 1, it will always have the shortest distance from that 0 as the previous neighbor followed the same rule. Okay, let's look at the code to get some action. We are going to start by defining the length of the row and the column. After that, we are going to import dequeue from the collections counter. Dequeue is a built-in data structure in Python which has functionalities like a queue. We are going to use it here because it is extremely fast to process the end elements, so the functions like pop and push become a lot easier. We start with dequeue to mark all the number of zeros we have in our matrix and then also keep track of our current indices from where we expand. The other data structure we are going to use is a set. Set is extremely fast to look up elements. It acts as a hash table and acts as a fast way to retrieve values from a memory. This is to store all the indices that we have visited so far. We start with iterating in the matrix and then check if an element was 0 or not. If it is, add it to our queue as well as the visited set. The concept we are going to use is to push and pop elements out of a queue. So we are going to continue iterating in the matrix if we have elements in the queue, and this can easily be done with the while loop. So when we pop the element, we use its indices to check up on its neighbors. The neighbors could be in four directions: top, left, right, bottom. If we have already visited the neighbors, then we do nothing and just continue. But if we haven't, we can check that by using this statement right here, where we are making sure that the index is in proper range in terms of the row and the column. If all the conditions are met, we add +1 to the distance. Some of the examples look like this. And then we add the new index to our queue and to the visited set. The first elements are always going to be 0. The next elements in the queue will always be 1, and the next one will be 2, and so on. So this makes our approach by default a greedy one, where we just take the minimum distance from 0 each time. We keep doing this while we have elements in our queue, And in the end, we just return the matrix. So some of the test cases look like this. And coming to the time complexity, the first one to find all the zeros that we have in our matrix and add them. So this will be dependent on the size of the matrix. So it will be O of m cross n. For the second loop, its runtime is going to be dependent on the number of vertices and edges in our matrix. So here the complexity will be O of v plus e. This is checking all the indices of our matrix. The space complexity, on the other hand, is dependent on the queue and the set, which will be the number of elements in the matrix. So m cross n. The space complexity will be O of m cross n. Okay, that was it for today's video. I had started from zeros to solve this problem. If you don't know where all the zeros are, what will you do to approach this problem? Please let me know in the comments below. There are links to similar problems in the description below. Check them out. And if you found my video useful, please like my video and also subscribe to my channel. And I will see you next time. Bye.